IoT Foundations. Fundamentals. IoT Foundations. Fundamentals is a comprehensive course designed to introduce learners to the basics of the Internet of Things, IoT. The course covers essential topics such as IoT architecture, key technologies, and practical applications. Participants will gain an understanding of how IoT devices connect, communicate, and function within larger systems. Through hands-on exercises, the course ensures learners are equipped with foundational skills to design and implement IoT solutions.
Welcome to the course. I'm Bruce Sinclair, an IoT business consultant dedicated to assisting top brands, manufacturers, and enterprises in shaping their IoT business and product strategies. In this course, we'll delve into the technical aspects of the Internet of Things, IoT. We'll start with an architectural overview, breaking down the key components of IoT. Next, we'll explore the concept of the software-defined product, a digital twin of the physical product that is essential for distinguishing IoT products from smart or connected products. Following that, we'll examine the hardware-defined product, including sensors, actuators, and embedded systems that collect data from the physical world. We'll then look at the network fabric that connects the software-defined product to sensors and external data sources. Finally, we'll discuss how to leverage external systems to enhance the data capabilities of IoT products. If you're ready, let's dive in and explore the depths of the Internet of Things together. What you should know. This is an introductory course with no formal prerequisites beyond a general familiarity with technology. A basic grasp of programming, IT networking, and data analytics would be beneficial. However, the primary requirement is a genuine interest in the Internet of Things. Let's begin. Architectural overview. The Internet of Things, IoT, is a sophisticated technology that seamlessly integrates into the business landscape. To start with, let's define it. IoT extends the reach of the current Internet into the physical world by connecting everyday objects. While the technological advancements in IoT represent an evolution, their impact on business is revolutionary. The hype around IoT is justified, as it is divided into two main segments: B2C, business to consumer, and B2B, business to business. B2C IoT focuses on consumer applications, while B2B IoT encompasses commercial, industrial, and infrastructure uses. IoT products can be categorized into smart products, connected products, and IoT products. In this course, the focus will be on IoT products specifically. Smart products, which have been around for over 50 years, incorporate embedded devices but offer limited value. Connected products, though longer established, have debatable utility beyond basic connectivity, like linking a dryer to a smartphone. IoT, however, significantly enhances product value by integrating deeper functionalities. Traditionally, engineering views IoT as a networking stack from media to application layers, which emphasizes infrastructure rather than value. Designers and system integrators often take a more user-focused approach, considering front-end interfaces, back-end systems, and enabling technologies. A value-centric perspective is more beneficial for understanding IoT. Before delving into technical details, it's essential to grasp the basics and then expand to the broader picture. From a business viewpoint, IoT products can be segmented into four components: software-defined and hardware-defined products, connected by a network fabric, and interfacing with external systems. IoT technology either collects data or transforms it into actionable insights. Data collected by hardware-defined products and external systems is transported through the network fabric to software-defined products, where it is analyzed and converted into value. This course will explore each of these four components in detail. The software-defined product. Software overview. The software-defined product, SDP, serves as both the core and the intelligence of the IoT product. It acts as a virtual counterpart to the physical product, encompassing discrete items, systems, or environments. The SDP is one of the four primary components of an IoT product, positioned between the internal data source, the hardware-defined product, and external data sources, external systems. These elements are interconnected by the network fabric. The SDP comprises two main parts: the cyber model and the application. Essentially, the SDP simulates the product's functionality and, alongside analytics, encapsulates the entire value of the IoT product. Often referred to as the digital twin, the SDP is a virtual mirror of the physical product. Similar to a software-defined network, it abstracts the physical hardware into a software form, allowing for reorganization and focus on critical aspects. The SDP is akin to the brain of a robotic vacuum, such as a Roomba or Neato. While the device remains a vacuum at its core, the intelligence is centralized in its brain, the SDP. This virtualization is a key differentiator between IoT products and other connected or smart products, empowering them with unique capabilities. Cyber model. In the IoT ecosystem, three crucial components are the cyber model, the application, and analytics. The cyber model is at the heart of IoT products, driving value by serving as the foundation for both applications and analytics. Unlike traditional software models, the cyber model is a dynamic, live representation that integrates real-world data from sensors and external systems. This creates a closed-loop system that continuously evolves and adapts. Historically, models have been used in various fields, such as computer-aided design, CAD, for representing physical objects like cars, or in computer animation and video games to simulate characters and their interactions within environments. The cyber model in IoT is similar but more advanced, as it uses statistical representations to handle the complexity of real-world data. For instance, instead of using a simple linear equation to describe a spring's behavior, the cyber model would use real-world data to create a more accurate statistical representation. This flexibility allows IoT products to be optimized for different objectives, such as reducing energy consumption or minimizing operation time. Unlike a single CAD model, an IoT product like a smart dryer might have multiple models to represent various aspects of its operation, such as drying time or energy cost. Despite being a critical component, the creation of a robust cyber model is often overlooked. However, it is essential for developing valuable IoT products that stand out from those that are merely connected or smart. Application. The application serves as a crucial component of the software-defined product, working in tandem with the cyber model. It interacts with both the cyber model and the analytics, collectively known as the trio of value and IoT. This trio provides functionality and interfaces for human and data interactions. The application defines the product's operation and features. To draw an analogy with video games, the application represents the game itself, while the model embodies the characters within the game. The application leverages the model to generate functionality and serves as a communication hub, interfacing with users and product owners, and managing data flow between internal and external sources, sensors, and systems. In an online video game, this data might come from game controller sensors or AI operated by a remote data center. Notably, the application is not centralized. It can be distributed across the network fabric, from embedded systems on end nodes to the cloud, or any remote server on the internet. Mastery of IoT application development is essential for value creation and must be a core competency for every IoT company. IoT value modeling. Smart and connected products dominate the Internet of Things, IoT, landscape, but they often fall short because the additional value they provide doesn't justify the increased cost. This is where value modeling comes into play, a structured three-step approach to creating valuable IoT products. Let's take an IoT dryer as an example. The first step is defining the value proposition, drying clothes quickly and efficiently while preserving their quality. Next, we quantify this value proposition by breaking it down into measurable components, such as ventilation and heat, both critical for the evaporation process in a dryer. The efficiency, in terms of time or energy, depends on variables like fan speed, drum rotation speed, load weight, heater and drum temperature, and electricity pricing. Identifying these variables helps determine the necessary sensors for the IoT dryer. It's crucial to understand that the model evolves over time as more data is collected, becoming increasingly accurate. With the IoT dryer modeled in software, we can optimize it for various objectives, such as minimizing drying time. We then configure the dryer based on these optimized variables. The final step involves analytics, which can be classified into three types: historical, analyzing past energy usage, real-time, monitoring and responding to current conditions, like overheating, and predictive, forecasting drying times. Value modeling sets IoT products apart from merely smart or connected ones. A smart dryer might have a chip to control timing, and a connected dryer might send notifications to your phone. However, an IoT dryer not only optimizes drying efficiency and cost but also integrates with a network of other IoT dryers, collectively enhancing their performance through shared data. The true worth of a smart or connected dryer is limited compared to an IoT dryer, which prioritizes value creation through comprehensive modeling and data-driven optimization. When designing IoT products, it's essential to focus on value modeling to transcend the limitations of merely smart or connected devices.
Thanks for joining our video. Would you be interested to know more? Please contact us to www.icertglobal.com or email to info@icertglobal.org.